cancels out. 0 equals 2a. Whoa. Is a actually equal to 0? A is equal to 0? I'm gonna double check. Yeah, there's no way. Yeah, that doesn't is equal to 0. Okay, weird. Let's let x equal 1. What the fuck? X equal to 2? What is going on? Did I do something wrong? I'm confused as fuck. Wasabi, you guys. Welcome to part 6, where we will be dealing with rational polynomials and partial fractions. We have our first integral, which is x cubed over x minus 1. So here, we're going to go ahead and get started with the geometric polynomial. So here, if you don't know the geometric identity here, whenever you have this, right, in algebra, this is actually equal to x, not n plus 1, n minus 1. And then it continues on until you end up all the way to 1, right? So here, that's what we want, except it will be like minus 1 plus 1, right? So that's what we're gonna do. So we'll go ahead and go into that. So we're gonna do a zero substitution, right? So we're gonna borrow a 1, x cubed minus 1 plus 1, right? It's minus 1. What this does is this part here, this will become x squared plus x plus 1. And then we have plus 1 over x minus 1, right? Instead of repetitively using zero substitution, we could just put this in terms of a geometric form. So here, we're left with this. Now we can go ahead and do our integral. Ln x minus 1 plus c. And that's it. Alright, so how do we deal with integrals like this? So now, again, I like to have my numerator similar to the denominator, like x plus 1, so that I could just cancel things out. Here I have a 3x, right? So 3x, I want 3x plus 1, right? I would want 3x plus 1 so that x plus 1 cancels out. So I would need 3x plus 3. Okay. So then let's add a 3. We'll add a 3 and subtract a 3. The reason why I don't care about this constant here is because constants are constants. Constants are constants, right? Constants are just constants. They're very easy to deal with. You just put them at the side of the integral and do whatever. So that's why I don't really care too much about the constants. The ones with x's, you have to like deal with. So, okay. So we need 3x plus 3. So that means we would add plus 3 minus 3 and minus 2, right? Our zero substitution, right? And then this you can go ahead, right? Because we purposely made it that way so that x plus 1 cancels out. So this is 3, and then we have negative 5 here, minus 5 x plus 1 dx. Okay, so then this is just 3x minus 5 ln of x plus 1. And that is your answer. All right, very, very fast, very quick. Zero substitution is super helpful and you have to get used to it. Okay, So now what? So here is where we'll dive into partial fractions. So we have x minus 4, right? And we'll go ahead factor that. So we have x minus 4, and then we have, if we factor this, we get x minus 2, x minus 3, right? Okay, cool. So what do we do? So I think the safest thing to do is to do partial fractions. And it's okay. It's quite safe to do partial fractions very fast here because these x minus 2 and x minus 3, those are like linear functions. So it's okay. So what I like to do is I'll go ahead and perform my setup, x minus 2, x minus 3, and just make like a fraction like that. So that's my setup. So that's my setup. It's a good practice to learn that setup when you're doing simple partial fractions like this. So I'm going to use the Heaviside method, and I think you should definitely learn how to use the Heaviside method. The Heaviside method is super, super fast, and it really does save you. So here's how it works. So we'll start from here. We'll have, so in order to make x minus 2 0, x equals to 2. Okay. So then we plug in 2 here. 2 minus 3, negative 1. All right, so we put it at the bottom. Right. And then we plug in 2. For the top, we plug in 2 at x minus 4. 2 minus 4, that's negative 2. Okay. Then you do the same thing here. All right. X minus 3 equals 0. That's x equals to 3. Okay. 3 minus 2 here, that's 1. 3 minus 4 at the top, that's negative 1. And that's how you do partial fractions. You're done. Okay. So then this is just 2 ln of x minus 2 minus ln of x minus 3. You could just literally just go straight from there. You're done. Very fast partial fractions, right? So that's the Heaviside method. I think Black Pen Red Pen made a video about that, more in depth. But we're going to be using that method a lot here in speed integration. So for partial fractions, we use Heaviside method. What do we do here? So that doesn't really, you can't really factor that nicely, right? But we have a quadratic. So when you have a quadratic like this, a quadratic polynomial at the bottom, we're going to force an arctangent. So what that means, to do that, we're going to complete the square. So let's go ahead and complete the square. Let's complete the square. Let's say this is a 1 times x. So 1 divided by 2, that's a half. And then a half squared, that's 1/4. Okay. Oh, okay, so 1/4, and then minus 1/4 plus 1, right? Okay, so now this is equal to x plus a half squared, and then here that's equal to 3/4. Okay. You see how we force an arctangent? So forcing an arctangent really helps. So we go like this, right? Sometimes, be careful. Sometimes when you complete the square, this will be negative, and it would not be inverse tangent. It will be inverse tang, and you would have to use that. Okay? All right, so we have that. Cool. So now here, so be very careful. We're going to be very careful here. Whenever you have something like this, x squared plus a squared, okay, this is equal to 1 over a inverse tangent of x over a. All right? That's what this equals. This is equal to 1 over a inverse tangent x over a plus c. All right, that's what it is. So whenever you have a number, like let's say if you have like a mysterious number like this, like it's just a, then it would be 1 over a, square root of a, inverse tangent, x over square root of a. Okay, because this has to be squared. That's why. So do not forget that. This tricks a lot of people. Okay, so don't forget that it's the reciprocal and it's square rooted. It's square rooted. Okay. So another similar thing is, so like sometimes you'll have like bx squared plus a. Then what you would have to do is you would need to isolate this x, right? You would need to isolate that x, so we'll go ahead and factor it out. So we have b, and we have dx, and we have x squared plus a over b, right? Then this would equal to 1 over b, and this would be the square root of the reciprocal b over a, okay, inverse tangent. Inverse tangent of x square root of b over a. Okay, and then of course you can definitely simplify this with like, you simplify this, right? So just be very careful with that. All right. So now with here, in this case, we have an easier case. So this is just equal, so 3/4. So that's 4 over, so square root of 4 over 3, that's 2 over root 3. Inverse tangent of x plus a half. So we have to multiply this. X plus a half. Root 3 plus c, and this would be our answer. And you're done. That's all it is. Okay. So just dealing with a format like that, you just have to practice a lot so that you get it into your memory. Yeah. So the reciprocal and the square root of it. Okay. Don't forget that. We have it factored, which is nice. But how are we going to do partial fractions with this? How are we going to do partial fractions with this? So this, we go ahead and do our setup. X plus 1, x squared plus 1. Now, here, this is a bit different. We'll have like that. We only do this when we have a linear function. Okay? Then we do this setup here. Here, this is not a linear function. This is it has a higher degree. So because of that, we have to do ax plus b. Okay, we have to do that. All right, so go ahead and start with do the Heaviside method with this linear function here. Okay. Oh yeah, because this is dx, this numerator is just 1. So you can just put 1 like that. Okay, because there's nothing here at the numerator. There's nothing here at the numerator, so you can just put 1. Because technically it's just 1 at the numerator. Okay, then we just go ahead, okay, this is -1. Plug in -1 here. That gives me 2. All right, a half. Cool. All right, but then how do we solve for ax plus b? This is where we have to do our the advanced setup here. So the numerator is 1. Okay, and then here we do the butterfly. Let me actually color this. We do the butterfly, right? This times this plus this times that. Okay, so we'll go ahead. A half times x squared plus 1. And then plus x plus 1, ax plus b. All right. So we need to solve for a and we need to solve for b. All right. let's solve for b, because for a, we can let, so here's what's going on. See how a is being multiplied by x? We can get rid of that a by letting x equal to 0. Let x equal to 0, and now when we let x equal to 0, that a disappears, and we can just solve for b. We can just solve for b. All right. So then let's see, 1 is equal to, let's see, 0, so that's a half, plus 0 plus 1, that's just 1, and then we just end up with b. Okay, so b is equal to a half. B is equal to a half. All right. So then, now that we know that b is a half, now you can let x be anything that you want to be. Let x equal anything, and then just solve for a here, right? Now, it depends. It depends what kind of stuff we have here. In most classes that you learn, they'll just say, oh, just let x equal to 1. I don't like doing that because sometimes we'll have nastier fractions, and I want to get rid of the fractions, right? Here, it's actually okay to let x equal to 1. I would actually put x equal to 1. And the reason why I would do x equal to 1 is because when I plug in 1 here, this fraction cancels out, right? Because it will be 2 times a half. Then x plus 1 here, right? 1 plus 1, that's 2. And this b, the half, gets canceled out, right? So let's go ahead, let x equal to 1. Then we get 1 equals, this would be 1 plus, let's see, 2a plus a half, right? This becomes 1 plus 2a plus 1. Cool, so no fractions. So pretty much what we have is 1 plus 2a. Well, it's technically 2 plus 2a, right? So, okay. And then we have negative 1 here equal to 2a. Oh, okay, so a is equal to negative 1/2. Got it. All right. Then I would use like my eraser on my left hand to sort of erase everything except those two informations. Okay, so now we know what to do. This is a half, x plus 1. And then we have a half x squared plus 1. Then a is negative half, so it'll be negative x here, and then b is positive. Again, I just took the half at the front. I just factored out the half. Okay. So what do we do now? If I separate this for you, right? This is actually a lot easier, right? So this is x plus 1 minus x squared plus 1 plus 1 x squared plus 1. Oh wow, would you look at that? A very simple integral now. So now we can go ahead, solve this. Okay, this is a half ln of x plus 1, right? This is a u substitution, but I'll just go ahead and dive right into it. This is minus 1/4 ln x squared plus 1, and then we have a half of inverse tangent plus c. Oh dear God, this is nasty. So what are we doing? Partial fractions? You're funny. No, we're not doing partial fractions. Here we have x squared plus 1. Ooh, let's utilize that. Let's utilize that. So we have x squared plus 1. And then, of course, this will cancel out. And then we have x squared plus 1. This is very good because we can just do a u substitution. Okay, So then this cancels out with this. Okay, so this is inverse tangent, right? And then here, plus, and then we let u equal x squared plus 1. Okay, so then this is a half du u square. Okay, we know this basic integral. So now this is inverse tangent minus a half of u, which is x squared plus 1. And that is our answer. Just like that. Simple. We don't have to do partial fractions. Dear God, no. It's just simplification, utilizing the numerator and putting it in a form like the denominator so that we, cancel things out and it simplifies. Okay, what do we do here? So this is very tricky. This is super, super tricky. Now, we have a very hard integral case here, right? You cannot factor this. Okay, you cannot factor that. And we like to complete the square. We only complete the square if we only have constants on top. But we have this x here. We have that x here. So let's say that we're not going to split it. We're not going to split it. So because we have this x here, so what I like to do is I like to force a derivative on top, right? And what I mean by that is I want a certain numerator where I can do the u substitution on x squared 2x plus 5. Then I want my numerator to be 2x plus 2. Okay. Cool. Oh, would you look at this? I could just make x plus 1. Okay, so I could just have an x plus 1 at the numerator. That 2 could just be half. So, okay. And we can actually take out that x plus 1 out of the 4. All right. Or to make it easier for you to visualize, we could just do we could just do 1 minus 1, a zero substitution. Okay, cool. X plus 1 minus 1 plus 4, right? And we know the denominator, right? So again, we purposely made it like this so that we could do a u substitution. So this is a half of ln x squared plus 2x plus 5. So we know what we're doing. Right, but then we have minus, I'm sorry, not minus. 4 minus 1, that's 3. Okay, and then complete the square here. We complete the square. Oh, this is just x plus 1 square plus 4. Cool. So x plus 1 square plus 4. And there goes my Discord. Okay. So I have to end task manager. So, and then like I showed you, here, this is equal to half ln of x squared 2x plus 5. And here this is 3 over 2. Okay. And then we have inverse tangent of x plus 1 over 2 plus c. And this is our answer. That's it. You're good to go. All right. So a lot of algebra manipulation we did there, right? We did a lot of algebra manipulation, but it's fast, especially if you know what you're doing. The whole purpose is just to, utilize, okay, we need to change that into two simple functions. Constants we don't really care about. That x we have to take care of, and then force a u substitution in a way. Yeah, that's what that is. So let's go ahead and do another Another example. Oh God. Ooh. Okay. So, there's no escape for this. Unfortunately, there's no escape for this. You could. It's gonna be advanced here. I'll show you. I'll show you the advanced way. All right, let's let this equal to I. Oh boy, why are we letting this equal to I? You'll see why. So we have 1, okay? We have 1. We know what the denominator looks like, right? We have it right here, okay? I want to do, let's see, I want to cancel out x plus 1, right? Okay, 1 plus x, and then you have minus x here. I want to cancel out x plus 2, x plus 2, but this is, remember that negative distributes. So then we have plus 2. Okay. Then we have plus 2 of the same denominator, right? But then this is equal. So just to help you visualize, we're left with this now, right? But this and this is the same integral. The only difference is that this is 2i. So I can just go ahead and put this here. 2i. Let's see. Plus 2i. I subtract it to the other side. I get negative i. Okay. And then that negative here, I can just divide it, or just bring the negative to the other side, and this makes this whole side negative. Okay, so what we actually have is I is equal, oops, so this negative here distributes everything, so we get positive x plus 1 square from this side, because the x plus 2 canceled out. And then x plus 1, 1 plus x here, which canceled out one of this. So we have minus x plus 1, x plus 2. Okay, a lot to process there. That was a lot to process there. Again, this is a very advanced move. It really was a lot to process there. And then here, this is just a simple integral. And then here, you just do partial fractions, Heaviside method. So that is the advanced method. But I will show you a more comfortable way. So let's get rid of this. So here, what we do in partial fractions, we go like this. Okay, so start with x plus 1, but because that's squared, we need another x plus 1 squared, and then x plus 2. All right, now in our setup, the way we do it, so in Heaviside method, it's the highest degree. We use the highest degree. And then that x plus 1, we don't deal with it at all. So we need it to turn it into a letter. And then we do the same thing that we did before. And the reason is because this higher degree beats this. So that's why we have to set it up like this. Okay, so and the numerator is just 1, so we can just go like this. 1, 1. Cool. All right. So plug in negative 1 here. Let's see, negative 1 here. This makes negative 1 plus 2, that's 1. So plug in negative 2, right? Negative 2, that's negative 1, right? But we're being squared. You are being squared. So negative 2 plus 1, that's negative 1. Negative 1 squared is positive 1. Okay, positive 1. Now that we have this, we need to solve for a. So again, to sort of help you visualize how to do this, is we take this chunk at the denominator and we reciprocate it to the other side, which will cancel some stuff out. Okay, so when we multiply this whole chunk to both sides, we get 1 here, and here we get a times the x plus 1 gets canceled out by 1 of this, so we have x plus 1, x plus 2, and then plus here we have 1, this x plus 1 squared gets canceled out with this, so it's just x plus 2, then plus here x plus 1 squared. Okay, so yeah, we have to find a. We have to find a, and here's something I need to let you know. X cannot be negative 1 and negative 2. You want to know why? Because if we ever have that, a disappears, and that's not good. That's not good. Our whole objective is to find a. But let me tell you something. We can let x equal to 0, right? Okay, let x equal to 0. So then we have 1 equals 2a plus 2 plus 1 squared. That's just 1. Cool. So then we have negative 2 equals 2a. Oh, a is equal to negative 1. Awesome! So a is equal to negative 1. We have a equal to negative 1. Cool. So we'll go ahead and sort of have everything all lined up. X plus 2 minus x plus 1, 1 over x plus 1 squared dx. Cool, this is just, we just go ahead and integrate it. Ln of x plus 2 minus ln x plus 1 minus 1 over x plus 1 plus c. And we're done. Alrighty, let's go ahead and sprint this out. Okay, x plus 1 plus x plus 2 plus x plus 4. Alright, setting up, doing my setup. Our numerator is just 1. Alright, cool. That's no problem. Alright, here, we have to be careful. Alright, there's more than one stuff that we have to deal with. So, because of that, we're going to do a parentheses here. Okay, alright, negative 1, plug in negative 1 here, that's negative 1 plus 2, that's just 1. Negative 1 here, negative 1 plus 4, that's 3. Okay. Alright, so that's how it works. Alright, plug in negative 2. Alright, so negative 2 here, that's negative 1. Negative 2 here, that's 2. Alright. Alright, here, we have to plug in negative 4. Negative 4 here, that's negative 3. Negative 4 here, that's negative 2. Okay, got it. So now my integral, this, I can go ahead and just straight up integrate 1 over 3 ln of x plus 1. Alright, this is negative half ln of x plus 2. And this is plus 1/6 of ln of x plus 4. Plus c. And but bam, look how fast Heaviside method is. Okay, that's how we do it in speed integration. Oh god, what is this? What do we do here? Okay, now, that bottom does not factor nicely. Okay, so then, what do we do now? What are we gonna do? We can do the same thing like we did before. We want to turn this numerator into the derivative of this, right? And the reason why I need to do that is because we have an x here. We don't know what to do with that x, right? We don't know what to do with the x. However, that x, so it's kind of like a pattern thing where it's like we have x squared and we have x. If the highest degree, then on the top you have like, I guess it's best if I write it like this. If we have something like this, like a polynomial of xn, right? And then I have something on top where it's like xn minus 1, then what I would do is I would force this, I would make this numerator the derivative of this, so that when I do a u substitution, I get like 1 over u, whatever, and then plus, and then whatever leftover you have, right? That's what I would do. If it was x to the power of n, then I would do a zero substitution where this is similar to this, and then we can cancel out, plus some leftovers that I had from the zero substitution, right? And then if I have x to the power of n here, and then I have a constant, then you would have to hope that this is nothing uglier than, you know, a quadratic polynomial, right? If it's a quadratic polynomial, you know, if it was x squared plus something, and there's a constant, oh, cool, complete the square. If it was a linear function, that's even better. We just do ln. If it was cubic, though, that's a whole different story. And most of the times, you won't get that. I mean, you'll only get it if it was like this, or something factorable, right? But if it was something like x cubed plus x plus 1, you will never get this in integration Bs. And if you do, something's wrong with the problem writer. But other than that, in this case here, I would want to sort of make this numerator like the derivative of here, so that I can do a forced u sub. Okay, it's not really a forced u sub, but technically I want to make it into a u sub integral. So if I want u to equal x squared plus 4x plus 5, then I need my du to be 2x plus 4. So I need x plus 2. Okay, no problem. So we'll go ahead, add a 2, minus 2, right? Zero substitution. So then, I'll put it here. Of course, don't forget that we did the thing. We did this, which means that we need a half. Oh, but I can just go into it. X squared plus 4x plus 5, right? And then we have minus 2. Complete the square. Go ahead, complete the square. This is x plus 2 squared plus 1 dx. Oh shit, look at this. This is just ln square x squared plus 4x plus 5 minus, and then here, this is just inverse tangent of x plus 2 plus c. All right, time for this integral. Ooh, let's see. We know x squared minus 4 factors out, so we can make that x plus 2, x minus 2. Okay, so it looks like we're going to have to do some partial fractions and splitting. All right, so make this x minus 2, x plus 2. Wait a minute. Wait, stop right there. Stop right there. I'm going to show you a sneakier trick. Okay. Look at this. So partial fractions is, okay, this is going to sound very based of me, but I think partial fractions is nothing related to calculus. This is just an algebra stuff, right? Partial fractions, this is all just algebra. All algebra, it's all algebra. Okay, so let alpha equal x squared. Okay, this is not a substitution. This is not a u substitution. Okay, otherwise I wouldn't be using u, but this is alpha. Okay, and this is just algebra related. This is just algebra related. Okay? It's just algebra related. Okay. And now this is okay, so now we see this as a linear function. Okay, no problem. Alpha plus 4. Alpha minus 4. Okay. And then our numerator is just 1. Plug in negative 4 here, that's negative 8. Plug in 4 here, that's 8. Okay, cool. And then you plug in alpha back. Oh my god, would you look at that? So much faster, right? So now you have, I can just factor out the 1/8 here, right? And now what you have is x squared minus 4 here, and then minus x squared plus 4 here. You are welcome. That's all you need to do. So it's a very sneaky trick, right? Because these are like the same thing, and then it's just, you know, a bunch of constants. We don't really care about that, right? So we could just do alpha substitution and then partial fraction like they're linear. Okay, so then so now this equals 1/8 of inverse tangent. Be careful, this is 1/2 inverse tangent of x over 2, and then inverse tangent. This is, let's see, that's a 4, so we need to reciprocate and square root it. Inverse tangent of x over 2. And this is your answer. And you're done. See, that's it. You don't have to take the long way where you factor this out. No. We just do this. All right, here's another good example. So here, I'm going to show you a very, very sneaky trick, okay? I want you to notice something. Right, when I multiply these two, I get x squared plus 5x plus 4. When I multiply these two, I get x squared plus 5x plus 6. Okay? So, that's what I'm going to do. So I'm going to well, actually, notice we have this here, right? If I let u equal x squared plus 5x, then my du is equal to 2x plus 5. Okay, we could actually do that. Or, if I want to cheat just a little bit, I could let u equal x plus 4. Right? So, okay, we'll do that. We'll let u equal x squared plus 5x plus 4. Then what we have here is du, because this gets taken care of. And then x squared, so here we have u, and then we'll have x squared plus 5x plus 4 plus 2. Right? So this 6, we need plus 4 minus 4, right? We use the 4 here, but here 6 minus 4, that's 2. So this is u plus 2. Okay. Awesome. And then, I mean, you could do partial fractions here. You could do that. I'm going to do the advanced way, which is I have 1. Well, this is u plus 2. I need this to be where it's 2 plus u minus u, so that this cancels out, and then for this one, this cancels out, you know? But I need a 2. How do I get a 2 on top instead of just a 1? So what you can do is you can do 2 times du. But because I multiply 2 here, I have to divide 2 here. Okay? And then you can go like this. Okay, so then this is 2 plus u minus u. Alright, so this cancels out and this cancels out. Awesome. And then, so I get 1 over u minus 1 over u plus 2 du. Okay, very tricky stuff. Very tricky stuff, but I'm showing you this now so that you are aware of it. It's like, you know, get you into the experience of speed integrating. So now this is just half of ln of, well, this is just u over u plus 2 technically, right? And then u is equal to x squared plus 5x, whatever. I'm going to go ahead and just write that all out. Plus 4 x squared plus 5x plus 6. Wow, that turns out very nicely. This looks like a bunch of e to the x's. So let's let u equal e to the x. And then we get u here, u squared plus 3u plus 2. Oh, this is partial fractions. Okay. Because this is u plus 1, u plus 2. Alright, cool. We'll go ahead and get into that. So now this is u plus 1, u plus 2, dash here, dash here. That numerator is not a 1, that's a u. So we cannot put 1 here. Okay. So let's go ahead. Plug in -1, plug in -1 here, that's 1. Plug in -1, u, it's just -1. Okay, plug in -2 here, -2 here, -2 plus 1, that's -1. -2, oh, I mean, it's just u, -2. Okay, so now our answer is just, well, this is, I'll put it here. We have 2 ln u plus 2 minus ln of u plus 1. So our answer is 2 ln of e to the x plus 2 minus ln e to the x plus 1 plus c. We have a similar type again, u sub, the u equal cosine of x. Then we get du of negative sine of x, so we'll have to do a negative here. Negative du u squared minus 3u. This factors out to u minus 3. Okay, so then we have u minus 3. That numerator is just a 1. Okay, u equal to 0. 0 to -3, that's -3. U minus 3 equal to 0. U is 3. Plug in 3 here. Okay, but don't forget that we distribute this negative. We distribute the negative. So now what we have here is this would become 1/3 ln of u, which is cosine of x, minus 1/3 ln cosine of x minus 3. So this looks ugly, right? But again, we'll just have to sort of do some partial fractions. Let's not hesitate any further, not waste any more time. Okay, x minus 2, x squared plus 1. Okay, so of course this is a linear function, so we can go here. 2, plug in 2, this is 5. Plug in 2 here, that's 2/5. Okay, then this is x squared plus 1, so we need to put this as bx plus c. Alright, so, and then now we go ahead and put it in terms, so take this whole chunk and reciprocate it to the other side. So we have x equals 2/5 of x squared plus 1 plus bx plus c, x minus 2. Alright, first of all, I need x to equal to 0. It's the first thing because I need to find c, and we have bx, so of course let x equal to 0. Okay, so then we get 0 equal 2/5 plus c -2. So I see we have negative, that cancels out, so 2/5 equals 2c divided to, oh, so c is equal to 1/5. Okay, so c is equal to 1/5. Okay, so now what? Okay, so c is equal to 1/5. So now that we know that c is equal to 1/5, plug in anything to find b. Well, let me tell you, I'm not letting x equal to 1. Okay, because of these 1/5, these fractions, okay, I do not want to deal with that. So instead, I'm going to let x equal to 2. Why on earth would I let x equal? Oh, shoot, no, I cannot. I cannot do that. Be very careful. Notice that I have x minus 2. If that will make it 0, and I will not be able to find b. So we cannot let x equal to 2. So then what am I going to do? What am I going to do? What am I going to do? Well, we can let x equal -2, but the thing is, this will make it -4, and c has a 1/5. I want this where I want to cancel out the fraction, right? How about, let's see, if I need this to be like, let's see, can I let this be -3? If I let this be -3, this becomes -5, and that can cancel out the fraction. If I let -3, this would be 9 plus 1, that's 10. Also cancel out the fraction. Awesome! Let x equal -3. Cool. Because then, okay, well, unless you don't like negative numbers, you could do 12. Oh, that's nasty. Deal with it. Okay, so -3. -3 is equal to, and then this is 10, so it's 2. Awesome. Right, and then -3 here, so we got, well, first of all, we have -5. And then we have -3b plus 1/5. Right? And then this becomes, okay, well, let me just deal with this first. This is -1 equal to, this is -5, we get 15b minus 1. Is it 0? I guess it's 0, so b is equal to 0. You do, this is possible. You do get things like this. B equals 0. Like, you do get things like that. And I guess that makes sense. That's acceptable because this could be 0, but you have this, you know? So that can happen. Cool. Okay. So then just write this out. That this is just 0, and then c is equal to 1/5. All right, cool. We'll go ahead and erase all this. So now our integral is, well, let me actually just dive right in. 2/5 ln of x minus 2. And then we have c equals 1/5, so we have plus 1/5 of the inverse tangent of x. Alright, 4x minus 2 over x cubed minus x. Huh, this is very awkward. Let's sort of factor this out a little more to see what the hell is going on. We have x squared minus 1. Oh, okay. Okay, then this is 2. The x minus 1 gets cancelled out by x squared minus 1, so we have x plus 1. Okay, cool. Here, we have x plus 1, But here we have a 1, right? You could just do plus x minus x. And this cancels out, this cancels out. Awesome. So then this would be 1 over x minus x plus 1 here. So now our answer is just 2 ln x minus 2 ln of x plus 1 plus c. Okay, don't be fooled. Don't be fooled. Yeah, just simplify it, and then if you can, you could do zero substitution. Again, be familiar with your squares. This could be into x plus 1 square plus 1, right? And then x plus 1 cube dx. Oh, okay, cool. This is just equal to 1 over x plus 1 plus 1 over x plus 1 cube. Okay, this is a linear function, so no, you do not have to do partial fractions. This is a u substitution, technically. So this is equal to ln of x plus 1, and then minus 2 x plus 1 square, right? This is just u substitution. I'm just doing it in my head. But yeah, that's how it turns out. So it's just basic u sub, and then you're good to go. A very common integration bee problem. This is equal to 1 minus x squared, 1 plus x squared. You know the drill, right? Alpha time. Right? We have x squares, alpha x squared, right? So then this becomes 1 minus alpha, 1 plus alpha, right? If the numerator is 1, alright. Plug in 1 here, that's a half. Plug in negative 1 here, that's a half. Okay, cool. So now we have, go ahead and change alpha back into x squares. Oh, very simple. This is just equal to half of inverse tangent plus a half of inverse tangent. And you're done. X minus 2. Ooh, what do we do here? Well, this is why I love things where it's like it's just x alone, because then I could just do a zero substitution. First off, I need the 2, right? Because I want to do 2 minus x plus x, right? So to do a 2, I will have to do a half, then a 2. Okay? So you multiply a 2, divide a 2. That's technically what I did. And then, okay, then I could go ahead, okay, I make it similar like this, so that this cancels out. 2 minus x. Then plus x, and this will cancel out this. Awesome. So now I have a half of the integral. This is negative when we cancel out because it's switched, right? And then here we have 1 x minus 2 squared, right? But we have this. What do we do now? Don't freak out. You can actually do it again, right? You can actually do it again. So if I can erase this, right? You can actually do it again, right? Multiply a 2 here, divide 2 here, minus x plus x. Crazy, right? All right, so then let me bring the positive side here. X minus 2 squared here, minus, and then here we have minus, this will be plus because this and this, they switch. So we have 1, 2x, and then here we have x minus 2x minus 2. Like that. dx. Okay, cool. Wow, we just did a zero-substitution inception. Okay, so now we have a half. I'm going like that, just for ease sakes. And then this is equal to 1 over x minus 2. And then we have plus half ln of x minus a half of ln of x minus 2. Plus c. And you can just leave it like this. And your answer is correct. Okay? Alright, last integral. Again, I love it when there's just an x by itself. Then I can do a zero substitution. Alright, so we have 1. We have 1 in the numerator. So I'm going to add plus x squared minus x squared so that the x squared plus 1 gets cancelled out. And here we have the x gets cancelled out. So, okay, cool, no problem. This will be 1 over x minus x squared. Only one of them gets cancelled out, so we actually have x over x squared plus 1. And that's actually, that's still good, because this is just a basic u substitution. So now we have ln of x minus a half ln x squared plus 1. And that's it. And you're done. So a lot of practice. We did go that very fast. And there was a lot of sneaky tricks that we had to do. A very, very tricky stuff here. But again, get used to zero substitution. Get used to completing the square. Turning the numerator into a du purposely, and Heaviside method. Okay, so a lot of tricky concepts there for speed integration, but with enough practice, you know, you'll definitely get used to it. You know, you can repeat this video and try it yourself, and yeah, I hope this video helps. The next part is going to be a last part, or maybe I might have to split this into videos, but the last part is the most serious integration bee part, and that is literally strategies, straight up hybrids of strategies of integration. So yeah, this is the real stuff. The next part is going to be some very serious stuff, strategic wildcard. Yeah, so subscribe to get notified for that, and I'll definitely see you guys in the next video.